All right, and we're picking up with the Taylor remainder. So it makes sense that if we have a function that's being approximated by this new polynomial, that there's going to be some sort of error somewhere. If we go to the 10th degree Taylor polynomial, that's still not a perfect approximation of the original. So no matter how far out we go, there's still going to be something that's different. If I subtract p sub n of x on both sides, then my error is equal to the difference of the function and the polynomial. Okay? Absolute value just keeps us in a positive light. So we know a little bit about this before we even get to the theorem. We know that the Taylor polynomial, the nth degree Taylor polynomial, would look like this. And remember, there's technically an x minus c to the 0 degree on that first term, but we don't write it because it's going to be equal to 1 anyway. We can say that f of x is approximately equal to what's in the box, but it's exactly equal to what's in the box plus this remainder. Well, the remainder, if it followed suit, would be equal to the nth derivative times x minus c to the n plus 1th degree, sorry, the n plus 1 derivative, n plus 1th degree over n plus 1 factorial. But you'll notice that there's a z value right here. And this is where I need to make sure that I get my wording right. If we plug in the c value that we're centered around, that may not be the best number to plug in for the exact answer. So we're going to assume that there is some number that when we take the derivative and evaluate at it, it's going to be figured out. And that z value is going to be some number that's between the x of the function and the c that we're centered about, okay? And we want to minimize the adjustment between the x and the c so that that error is so small, and that's going to affect our z value. I said that terribly, so I apologize. But here's what it looks like. Again, I'm going to have to do it on paper because I've got a mess on my notes. So technically, this should probably be labeled example. Let's see if I go back. Example 7, although it's technically example 6 because we skipped one. All right. It says determine the degree to which the p sub n of x, the Taylor polynomial, nth degree Taylor polynomial, should be expanded, and that should change to c equals 1, so that the error for the natural log of 1.3 is less than 1/10,000. Okay. First of all, here's what I do know. If I'm told to find the nth degree or to do anything with the nth degree Taylor polynomial, then I need to go n derivatives, but that's not realistic. I don't know what n is. So I'm going to go as many derivatives as I need before I can identify a pattern. Okay? I start with 4 derivatives. And I apologize because the notes don't lead you to believe that I'm doing 4 derivatives. It just kind of has a summary of patterns. And yeah. So the derivative of the natural log of x, that's what I'm looking at, right? That would make sense if I'm trying to evaluate natural log. So we're going to look at the function natural log of x. Natural log of x, we already know its derivative is 1 over x. Oops. We know that that becomes negative x to the negative 2, positive 2 to the negative 3, negative 6 to the negative 4. Okay, and we see, hopefully we see some patterns. Hopefully you recognize that the coefficient and the exponent become the coefficient of the next one, and we have an increase, or I guess a decrease in the exponents, or you could think of it as an increase in the exponents in the denominator. Just to go out a few more to make this a little bit easier, or I'm just going to go out a few more couple more to go to make this pattern a little bit easier. So we've got 24x to the negative 5. We've got negative 120x to the negative 6. And I want to summarize the nth derivative, but also the n plus 1th derivative. I feel like the n plus 1th derivative, which is what we need for our formula, will be much easier once we know the nth derivative. So let's look at maybe the 4th derivative here. The 4th derivative has a 4 in the exponent. The 5th derivative has a 5 in the exponent. So I know that the nth derivative is going to have x to the negative n in the exponent. I also know that my coefficients are a pattern. First of all, they are alternating. The very first one is positive, then it becomes, or I'm sorry, the first derivative, this can get confusing. When I have a first derivative, it's a positive coefficient. When I have a second derivative, it's a negative coefficient. So that number is opposite of its placement. Like if I wanted negative 1 to be, let's say, well, basically just plug in something. If I have a 5 here, it's going to be even, but I won't have an even exponent if I put, or I won't have an even, sorry, I won't have a positive 1 if I put n here, because the 5 exponent would give me a negative number. So I'm just going to adjust it by either adding or subtracting 1. I made that really difficult. Sorry about that. The other thing to keep in mind is what is actually happening with the coefficients. 1, 2, 6, 24, 120. How do those numbers connect with what you see in the exponent, or connect with what you see as the derivative? Well, hopefully you recognize these numbers as being factorial numbers. And hopefully you realize that the number isn't the factorial of the exponent that you see, but rather the exponent from before. 24 is 4 factorial. Well, if this is the 5th term, but I want 4 factorial, then I'm not going to do n factorial, but n minus 1 factorial. Actually, I don't like this x to the negative n over here. I'm going to write it as x to the n in the denominator. All right, so if that's the nth term, then what's going to happen for the n plus 1th term? Well, I can either write negative 1 to the n plus 2, or if I had originally thought of this as n minus 1, then I can make this look a little bit simpler by just saying n. It's 1 away from the 1 that we just did. In other words, if this is an odd, then I made this one an even exponent just by being 1 different than it. Well, if I increased and went from n to n plus 1, then this is going to increase to n factorial over x to the n plus 1. Okay? This is my formula that generates my nth term. It's also the formula I would use for the Taylor series. Or I guess this wouldn't be necessarily a Taylor, whatever. Okay, but you know what I'm talking about, hopefully. So here's where it gets a little bit complicated. It says on the previous page that r sub n of x is equivalent to f to the n plus 1 of z times x minus c to the n plus 1 over n plus 1 factorial. Better yet, if I want it to be a positive error, I'm going to put parentheses or absolute values around it. I'm going to plug in what I know. F, or the n plus 1th derivative of x, is this formula. But the n plus 1th derivative at z would be the same formula, except z would be plugged in. Okay? My x minus c, well, what is x minus c? Well, the original problem is asking to find the error from 1.3 to the point that we're centered around. There's my c value, so that's my x value. Okay? This is equivalent to the error for this Taylor polynomial. And we want to know what the nth degree should be so that our error is minimized at 0.0001 or less. In other words, we're going to try and make this less than 0.0001 and solve for n in the process. So keep that in mind. And I'm actually having a different kind of thought as I'm going about this. So bear with me if I say something weird. I always say something weird. All right, so let me simplify a little bit of what we have in front of us. I'm going to bring that z down. Okay. Hopefully you also see that n factorial and n plus 1 factorial differ by just that n plus 1 factor. So that n factorial and that factorial symbol can cancel. I'm also going to play around with this 0.3 to the n. Okay. If I apply absolute value to that, the only thing it's going to affect is this right here. So I can look at this as, I guess I don't need to split this. I don't think that helps in my math. 0.3 to the n plus 1 over z to the n plus 1 times n plus 1. Okay, so let's go back to talking about z. Z is supposed to be a number somewhere between the 1.3 and the 1. And we need to figure out what that z should be so that we have minimal error in this situation. Now, if z is between and possibly equal to 1 or 1.3, which one of them would maximize this issue so that we would basically be analyzing our worst case scenario? Well, if I have the smallest of the numbers in the denominator, it's going to create the biggest possible fraction. Which then, if I create the biggest possible fraction and I can squeeze that to be less than or equal to 0.001, then I'm good to go. Okay, so I'm going to use a z value of 1 to maximize this error to squeeze it underneath this restriction. And we know that 1 to a power is still going to be 1. At this point, the rest of what I'm going to be doing is just basic rules of algebra and some manipulation of fractions and stuff. I see 0.3 as being 3/10. And I'm splitting it off from the denominator. The reason I'm doing that is because, and by the way, I'm going to change this to 1 over 10,000. Because if I multiply by n plus 1 on both sides, then I can flip this. Okay, I'm getting kind of crazy. I can flip this. Hold on, I'm going make sure that I'm saying the right thing. This is where I'm getting caught in my words. Okay. I didn't need to bring that over at all. So let me go back one line. I'm still going to treat this as 3/10 to the n plus 1. I am going to treat this as 1 over 10,000. Okay, so I actually am going to multiply by n plus 1 on both sides so that I can manipulate this fraction over here. And there is reason behind that. Okay, so multiply by n plus 1, both sides. And if I have a fraction that's less than or equal to another fraction, then if I flip those two fractions, this will still maintain its equality. For example, if I have 2/5 is less than 8/3, or actually it doesn't, it's going to flip there. 2/5, 3/8. Okay. Right, because we're raising it to a -1. All right, so let me check again with my notes. Yes, okay. All right, so if I change this to 10/3 to the n plus 1, it's going to change this fraction as well. If you go back to the original question, it says determine the degree to which p sub n of x should be expanded so the error in approximation is less than. Okay, so I'm going to bring this n plus 1 back. Oh, goodness gracious. The math made total sense when I was looking at it a second ago, and now it's all weird. Okay, I guess all of this stuff is kind of irrelevant in that case because what's happening is that we need all of this to be greater than or equal to 10,000, right? The only way that that will work, well, plug in some numbers for n. Now that everything's on one side, plug in some numbers for n until we get to a number that's greater than or equal to 10,000. You know, what would happen if n is 1? If n is 2? If n is 3? If n is 4? If I plug in 1, I get 22. That's not big enough. So if I plug in 2, that's not big enough, but it's getting better. If I plug in 3, that's not enough, but it's getting better. 4, getting better. Still not above 10,000 yet. Oh, we're getting real close. Okay, at that point we're above 10,000. So the n value that we would have to use to minimize our error ended up being a number that would have to give us a total greater than or equal to 10,000, and that number was 6. So we would need a 6th degree Taylor polynomial to approximate that within the error that we wanted. Okay, that means that we wanted error from our graph approximation to the original curve to be so minute, the error to be so minute that it would fit into this less than or equal to 0.001. 0.0001, I apologize. So there you go. Remainder, it was a train wreck, but it is what it is. You will not